All right. Well, welcome back, guys. I hope you had a good Thanksgiving. This is welcome to class number 119 of CS205A. You're almost there today and Wednesday, and then we're complete. So anyway, we're gonna your last official homework is due today, and hopefully you saw on Piazza that I posted an optional homework 8. The deal is that this homework is completely optional. If you don't want to do it, then don't even look at it. Totally cool. But I always say this, I don't think it's quite as hard as the ones before it. Whether you think that or not is up to you. And I would recommend at least trying the first problem on homework 8, because I think it's good review of these sort of ODE integrators that we talked about 2 weeks ago. And it really is, the calculations are pretty straightforward. The code, I think, averages about 2 lines per problem. And in the end, you get to simulate a bunch of springs moving around, which is kind of fun to watch. Cool. So, alright, so we're almost done with CS205A. So I put my whole laundry list of different announcements for you guys so that I wouldn't forget, because the usual end of quarter hectic mess is upon us. So, so your homework 7 is due today. If you'd like to use late days, you can go for it. If you don't want to use late days, that's even better for us. But you can hold us to our word, and that's totally fine. You have this optional homework 8, which is due on this is great, they put the TV on that day, on the 9th. And you can do that if you like. The deal is if your grade is better than your grade on one of the other homeworks, it'll just replace it. I think that's pretty standard for classes like this. The last lecture is this Wednesday, and it will cover partial differential equations part 2. Your last section is this Friday, and presumably it'll be final exam review. Yeah, I don't know what else it will be. And your final exam is on the 12th, and I have no idea why, but the CS department put your final exam in Gates B3. So I'm going to send you about 4 billion reminders of this fact, because I think it would be really easy to show up in this room by accident, but it is not in this room. It is in Gates B3. Cool? Yeah? Nods? Everybody? B3? Okay, I'm going to do this again at the end of class today, and again in class on Wednesday, and on Piazza sometime this week, and on Piazza right before your final, because I really don't want to deal with people that went to the wrong room. Cool? Alright. Good. So, as always, I suggest you come to office hours for help. I'll try and schedule a couple extra office hours next week before the final exam, and maybe we'll try and come up with a reasonable schedule, given, I think a lot of you guys are all in a similar sort of set of classes, right? 221, 229, 148, or 248, whatever. So I'll take a look at when those are and try and schedule around them. Any questions before we proceed about, procedural and core stuff? No? I think it's pretty straightforward. Great. So I'm supposed to remind you that your course reviews for this course are I started this sentence without a verb, but what I'm trying to say is that you can post your course reviews starting now if you like. Stanford has a course review system. I think it's, having been here for 8 years, I should know this by now. You go on Access and there's some button and you click it and you fill it out. As you've probably seen, this is the first time that I have taught CS205A. Given all of the hopefully comedic struggles that we've had in this course, but hopefully you still learn something in the end. There are obviously lots of things that can improve, and hopefully lots of things that are improved from previous offerings of this course. So your input is very much appreciated. If you have, I think the questions on that form are a little generic and terse. If you have additional comments, please, by all means, email them to me, and I'm a pretty enthusiastic guy about teaching, and I will definitely read them and probably incorporate them into future offerings of whatever CS205A becomes in the future. Cool? Alright. One other thing, I emailed about this yesterday, and that's I have a request for your help. So, these course notes that I've been posting for 205A, obviously they've been happening by the seat of our pants, especially in the last 5 weeks, because it's a they say the best way to learn how to write quickly is to just write all the time, and I've had the pleasure of writing 15 pages of math every 4 days for the last 3 months. So in the end we have a textbook, and CS205A, you might have noticed Heath doesn't quite parallel what we cover in this class, and certainly has sort of an engineering perspective as opposed to a computer science one, which is slightly different. So anyway, these course notes most likely will appear as a textbook at some point in the future. but they need a lot of help to do that, and so you can read your email for some more details, but if you'd like to help out with that, I can offer some sort of independent study units next quarter in the spring to help go through chapter by chapter, provide some implementations, and understand this stuff a little better. I think it'll help you solidify your knowledge of this class, and will help you with the obvious tasks that I need to get to. Right, so anyway, so that's all of our procedural stuff, onto the interesting things. So, I know that our last lecture was 2 weeks ago, which is a really long time, so we're going to go back through and help you recall exactly what we were doing once again. So, remember that the last 2 weeks of CS205A are all about differential equations, right? So we spent about the first 7 or 8 weeks of this class solving assorted problems where your unknown is basically either a number or a vector, right? When we're solving these optimization problems, we want to minimize something, we want to solve AX equals B. All the time, our big goal in all of these algorithms, from a very generic standpoint, is to find an X minimizing or something, or satisfying some system equations and so on, right? But now in the last couple of weeks, starting with our lecture on interpolation, and then we did, quadrature like what's on your homework today and so on, our unknown is actually a function, right? And so we've had slightly different techniques for dealing with this. And in particular, last time we spoke was all about the idea of a differential equation, right? Where we write down relationships between the derivatives of a function, and then we want to figure out what the function is based on those relationships, right? And so when we talked about ordinary differential equations, or ODEs, right, we define this idea of an initial value problem, right? Where our job is to find some f of t, right? We usually think about t as time, right? Because our big intuition of this comes from Newton's second law, probably. And the idea is that it takes in a number t for time and gives you a point back, possibly in Rn. Like if you choose to do homework 8, then what this is going to do is f of t is going to be the position of like 10 different little particles of mass floating around on the plane that are connected by springs, right? And so f of t is going to be the positions of these guys over time as they move. Yeah? So your job is, given some relationship, big F, that ties all of the derivatives of f together, you want to find f for all t, given what it is at time 0. I think this is a pretty reasonable problem. And again, our intuition for this comes from Newton's second law. Right? The Newton's second law really is a relationship between the second derivative of where our particle is moving around, right, the acceleration, and some things that we can gather from the physical setup we have, right? The set of forces is just based on the positions of all your particles, right? So if, for example, again, on your last homework, I'll have you actually work out F equals ma. I know that this class doesn't require physics, but I have full faith that you can figure this one out. Where basically all you're going to do is sum up a bunch of spring forces that come into a point, which is very easy, just summing up a lot of vectors. And we're going to assume everything has mass 1, and it's as simple as it gets. Anyway, so this week we're going to consider problems that are a little bit harder. And by a little bit, I mean ridiculously hecka harder than the ones that we talked about 2 weeks ago. And those are going to be partial differential equations instead of ordinary differential equations. Now, the interesting thing about PDEs, which is a little bit different from everything else we've covered in this class, is that CS205A does not have as a prerequisite any course that covers anything involving PDEs. And I'm aware of this. And because of that, we're going to spend most of our lecture today talking about sort of theoretical aspects of PDE and how might you formulate them and use them in everyday life. And then at the end of class, we're going to talk about discretization, and we'll continue that on Wednesday. And I'm thinking on Wednesday since obviously the PDEs actually are also the topic of a year-long course in the CME department. Obviously in 2 lectures, we will get nowhere close to what they do, but we will summarize some ideas, and I'm thinking maybe I'll grab a couple sort of big methods from different parts of graphics and optimization and do them in a little more detail. Right? One of these like semi-Lagrangian advection fluid, whatever the heck. But anyway, there are lots of reasons why you might want to solve a PDE. Believe me. And some of them I listed right here, and then we'll do a bunch more in just a moment. For example, I'd say one of the main ones that I know gets a lot of interest from computer graphics students at Stanford, especially those that really secretly wanted to take 205A from Ron Fedko, who does this for his research, is to be able to simulate fluids like smoke and water, right? And one property of smoke that I think is 100% reasonable, even if you've never taken a fluid dynamics class, which I certainly have not, is that fluid wants to move from areas of high pressure to areas of low pressure, right? Because if you pack in a bunch of stuff, then it wants to expand, yeah? Well, if you think about it, how does the fluid know what direction the pressure is decreasing? Well, effectively, it's taking the gradient, right? Your fluid is doing gradient descent on the pressure, yeah? Well, what does that mean? That means that the time derivative, right, how your fluids are moving around over time, is related to the spatial derivative of your unknown, which is pressure, yeah? So all of a sudden, the machinery that we have from last week no longer, at least immediately, is relevant, because we have derivatives both in x and t, but we only know how to deal with a single variable at a time so far. Yeah? Now, even if you're not interested in physics, there are plenty of applications of PDE outside of physics. One very common one, and one that continues to be a very active area of research, is image processing. And this is a totally reasonable application of PDE, because chances are, if I'm writing the next great Instagram filter, and I want to smooth things out and write this as some relationship between pixels, chances are I'm going to want to treat the horizontal and the vertical direction symmetrically. Okay? But those are two different derivatives, the derivative in x and the derivative in y. Right? So most image operators are going to have to couple these directions together. And once again, this nice time-stepping initial value problem setup that we had from last time doesn't apply. So there are plenty of situations where initial value problems really are what we want to solve, right? Like f equals ma, which is like, arguably the beginning of all research starting in like 1720, whatever the heck, when Newton came up with it. But sometimes you don't get so lucky, and in those cases you need partial differential equations. But as we'll see, the theory of PDEs is far, far less encouraging. Right? There was a slide that passed by very quickly in Monday's lecture 2 weeks ago, which was this fundamental existence and uniqueness theorem for ordinary differential equations, which basically said that for any reasonable ODE that you write down, it has a solution. That does not exist for PDEs. And there are plenty of very simple examples of PDEs that you can write down that are not solvable. And there are plenty of PDEs that you can write down that we don't know, either as mathematicians or as discrete people, whether they should have solutions, right? And so in fact, one thing people will do is say, well, we don't know if it has a solution, but I plug it into my discrete PDE solver and it gives me back something reasonable looking, so I think it does. But obviously that isn't a proof, and there's some very scary things that can happen there because your algorithms have no guarantee of functioning. Yeah? So anyway, this is just something to keep in the mind, that it's very easy to write down PDEs that might solve a problem that you think you should solve, just because it's kind of a nice modeling tool. But you had better do your homework and make sure that thing has a solution before you get too far down the road. Okay, so anyway, the big vocabulary word for today is partial differential equation, PDE. Yeah? The 2 weeks ago we talked about ODEs, or ordinary differential equations. By the way, if you're taught to a very fancy advanced mathematician, they might refer to what you might call an ODE as also a PDE, because it kind of sort of is, just in one variable, right? This is kind of a stupid thing. That always confused me in college. Alright, so I realize now that this slide has a lot of things on it, but I will break it down for you because it's quite simple. These are operators that you probably saw in Math 51, but I'm guessing we might need a little bit of a review here. And these are very common differential operators on functions in Rn. And they appear in almost any PDE that you can write down for physics, so they're worth highlighting a little bit. And that's div, grad, curl, and the Laplacian. Yeah, how many of us have seen 2 out of 4 of these? Yeah, okay. Cool. Right, so the idea here, right, as memorialized at the top of this slide here, is that let's say that I have a function f, right, and I'm only going to worry about the case on R3, but a lot of these are very easy to extend to higher dimensions, with the exception being curl. And if you're curious how to extend curl the proper way, you can talk to me after class, because this happens to be my research area. But that aside, the rest of these are totally, you just kind of pop additional terms on the end and they're fine. Yeah? It is that we want to be able to understand functions, f, right? Things that take points in R3 to numbers, that's a function, hopefully you agree with me. And vector fields, right, which assign to each point in R3 a vector in R3. Do you guys know, you have the right picture in your head for what a vector field is? Let's say that I'm in R2, then, for each point in R2, it gives me another point in R2, which I think of as a vector, right? The vector field is just attaching lots of directions to points in the plane, or in 3 space, as the case may be. Yeah? And basically, all these tools from multivariable calculus give us different ways to analyze and understand vector fields. And they're linked together in all kinds of very intricate, clever ways that we will not cover in today's lecture. But, for example, the gradient of a function, hopefully by now you know what that is. If you haven't, then we should do some very serious final exam review. But the gradient of a function is nothing more than a vector field, right? It's one way to think about it, where at every point x, grad f at x points in the direction that f is increasing the most. Yeah? This is one that we're used to already. The other three we haven't used so much, but they show up in PDEs a lot. So the divergence of a vector field is how much that vector field is spreading out. So you know how the gradient goes from functions to vector field? The divergence goes from vectors to scalar functions, right? And these things are linked together, right? If you Google it, do ROM cohomology, you'll learn all about that. But there are two pictures that you should have in mind for div, grad, and curl, and I will draw them here because I was too lazy to put them in the slides. And those are vector fields that look like this. One, a vector field that kind of cycles around a point. Yeah? And one where the vector field points outward. Yeah? Yeah? Okay. So I think with these two pictures, and I can draw sort of paths around these vector fields. Yeah? These two pictures, it's pretty clear what div, grad, and curl measure, right? In particular, what order did I put them in? The divergence, div of v, right? So again, it takes in a vector field and it gives back a number at every point in space, right? The divergence is measuring how much a vector field spreads out. Yeah? So for example, in this vector field where everything is kind of pointing out from some center point here, this vector field has high divergence, right? This is all, it's diverging from this point. Yeah? These are very smartly chosen words. And alternatively, this vector field here, right, it's all kind of spinning around a single point, has zero divergence. Right? Because nothing's spreading out here, it's all just kind of cycling around. Does that make sense? So, and right. The curl of a vector field gives back another vector, and basically the idea of the curl is it's measuring the opposite, it's measuring how much it circulates. Right? And the reason that it gives a vector back is it's actually giving the axis of the circulation. Right? So for example here, this vector field, the curl would have an axis that's pointing out of the board, right? Because everything is circulating around this point. So anyway, div, grad, and curl are totally reasonable things, and the Laplacian, we'll come back to why what physically the Laplacian means in just a few minutes. But the Laplacian is basically you take all of the second derivatives of f and you just sum them up. Yeah? Okay, so hopefully we all understand at least how you might compute each of these operators and have some picture in our head of what div, grad, and curl are doing. By the way, there is an excellent book in physics that is literally titled Div, Grad, Curl, and All That, which draws pictures of all these things and goes through all the details, and I highly recommend it if you like this sort of math, which is absolutely beautiful and geometric and topological, by the way. You can get like the number of holes in a surface by looking at vector fields, which is kind of cool. All right, so one very common notation, for one more slide of kind of generic stuff before we dive into PDEs. One very common piece of notation that we use in this type of field is we think about this triangle here. In LaTeX, this thing is nabla, right? This gradient operator. We think of it as an operator, right? So I made this kind of glib definition here, right? That this triangle without any f next to it is equal to a vector of 3 partial derivative signs. And this should not parse in your head, but it kind of looks like math, and your brain is kind of okay with it, and that's actually okay. And we can go back and double check all of our favorite formulas, and notice that this notation is totally reasonable. So let me copy it over here. I'm going to use x, y, and z instead of x1, x2, and x3 because I'm lazy. And so you have d over dx, d over dy, and d over dz. Right? Now this is just notation, right? There should be a triple equal sign here because I have defined this object. By the way, I think my notes are totally inconsistent about this, but I tried to. Anyway, so why is this notation useful? Well, let's say I want to find the gradient of f. Let's think of this as multiplying this triangle and this f, and in fact you get the right formula, right? Because you get d over dx times f, which is df dx, right? df dy, df, dz. Yeah? Similarly, if you want the curl, or rather the divergence of a vector field, right, we can write that as grad dot f. And in fact, well, that works again, because you say, sorry, this should be v, right? Well, so what is v? Well, v is like v1, v2, v3. And now I'm going to take the dot product of these three things. And what do I get? Well, I get dv1 dx, right, plus dv2 dy plus dv3 dz, which is exactly the formula for curl. Yeah? It's a very slick notation. That's all it is, just notation. Yeah? And in fact, I won't check the formula for curl, but you can see that it kind of looks like a cross product, right? And in fact, it works out. Yeah? And there are very deep sort of physical reasons why this notation is a totally reasonable one. All right. Oh, and finally, the Laplacian grad squared of f. Well, this one's a little bit. This notation's a little weird, but if you think of grad squared as sort of being this gradient vector dot itself, then this notation does work out. But this is just common, physicists use it, so we're stuck with it now. So does everybody understand sort of when you see this triangle, what it's telling you about a function and how you can use it to compute derivatives? Nods? Yeah? Okay. Cool. All right. One final thing, which just to make things a little bit more irritating. Now in physics, usually we have 4 variables that we solve for. We're not going to do, by the way, we're not doing relativity today, and we're not doing things with imaginary numbers, quantum stuff. We're sticking totally in F equals ma land. Right? So usually we have 4 variables, right? X, Y, Z, which is space, and then a 4th one, which is time. And usually in physics, when you think about this gradient operator, you think about it as, like if you were to follow my notation here, you might stick a d over dt at the end of this, but in fact, physics people don't. They think of this as a spatial operator. Cool, so this is just all notation. And it's going to simplify our discussion quite a bit today. All right. So, I thought I'd dive right to the hard thing, which is possibly the most difficult PDE that you can write down by a lot of accounts, and this is also the one that I would say most people that study PDE and simulation really care about, which is the NichollsStokes equations. How many of us have heard of this one before? That's this very famous set of equations. Okay? So the NichollsStokes equations are all about how to simulate, or really just how a fluid interacts with this environment over time. Right? So if I have a fluid like water, I guess. I wrote the incompressible NichollsStokes equation here, by the way, which means that I can't like smash my fluid into very small space. If you're dealing with gases, you have to be more careful about it. That PDE is even harder to solve. So the incompressible NichollsStokes equation basically has a bunch of different quantities that all have to do with your fluid interacting over time, and couples them all together using this humongous pile of derivatives to tell you how to simulate your fluid. Yeah? So you can see there are lots of different variables here. There's the velocity of your fluid, the density of your fluid, the pressure of your fluid, and external forces. Right? And the picture that you should have in your head is that literally I have like a fish tank of water, right? And the fish tank, by the way, we're not going to worry about the surface of the water as a whole other thing, and surface tension is an interesting problem that we're still working on. But let's say that I fill like a jug of water and I cap it, right? Then at every point in the water, there are lots of different things I can write down. For example, maybe I've taken my jug of water and I've shaken it around, whatever. And so in the end, yeah, my bucket of water is filled with water, but the little water particles and molecules are actually moving in the interior, right? And so because of that, I have some velocity vector field that's in the inside of the water that's showing how all the molecules are moving around, right? There's also pressure, which might vary from point to point, right? For example, like squeeze the sides of the water jug or something. And the density of the water, so on, right? So the NichollsStokes equations couple all of these different variables together to tell you how they interact and change over time. Yeah? As you can imagine, this is a horrendous PDE to solve. Why? Well, it's nonlinear. You can see that there's a product between rho and some of your other variables on the left. You can see that there's a ton. This equation that I've written on the top here is very slick looking, but it actually is a system of equations. right? You can see that you have different vectors that are all interacting over time, and so on. So you are solving a system of PDEs that are nonlinear in a bunch of variables. Doesn't get worse than that. But this is the equation we all care about. So there's a huge literature on fluid simulation, and we'll talk about some of the clever tricks that people use on Wednesday for doing at least very simple versions of this simulation. So one thing that I should note here, which is a good example of what I was talking about before, I've put a lot of thought into this, and if you can solve the problem on the board, I will gladly give you a few late days in this course. But basically, there is an outstanding mathematical problem, which is in 3 space dimensions, like the ones that I'm in right now, and time, given an initial velocity field, prove or disprove, we don't even know, that there exists a velocity and a pressure field that are smooth, globally defined, and solve the Navier-Stokes equation. Put another way by my professor, my PDE professor back in the day, prove that water does not explode in a finite amount of time. And if you can do that, you will earn yourself $1 million. And this is one of the largest outstanding problems in mathematics. That is, I wrote down this very slick system of equations, which you can actually derive just by looking at Newton's second law and looking at little parcels of fluid mass moving around. Right? So the equations are easy enough to write down, but we have no idea whether or not they are solvable. Now obviously, we write down lots of simulations that start with the Navier-Stokes and discretize them in various ways, and we get reasonable looking fluids, but we don't know if there's some really bizarre configuration of water where you put it in just the right place in a really strange gravitational field or something, all of a sudden your water explodes and the universe collapses and the singularity happens. We don't know. So anyway, if you can prove otherwise, then you make yourself $1 million, or if you find a counterexample, then either you're the evil overlord, or it shows that the Navier-Stokes equations are subtly wrong, probably at some molecular level that's not modeled very well by F equals ma. Yeah? Anyway, I only mention this to tell you that discrete PDE is a really weird field, and that usually, for example, last time when we talked about solving ordinary differential equations, right? At least in the back of our head, we knew that the thing that we were solving was actually solvable. Here, we will blindly write down discretizations of certain PDEs, and we might not even know that we really should be doing that. We might get reasonable looking behavior because we chose a reasonable PDE, but there's missing theory, and that theory is really, really difficult. Yeah? Okay. To move on to other examples of PDE that we all know and love. Another that you may have seen if you took an electrostatics, whatever the heck, physics 62, I think? That was the last physics class I took at Stanford. Is a set of Maxwell's equations. So here now you have an electric field E and a magnetic field B, and this tells you how they all interact over time. You can see that these equations tell you something about the divergence of E, the divergence of B, the curl of E, and the curl of B. Very nice set of equations. Obviously, we're not going to derive this in class because it's very far outside the scope of what we do. But one that we will describe in class in quite some detail is Laplace's equation, or sometimes Poisson's equation, depending on who you talk to. Now, this is actually a very simple version of this is on your homework due today. So I suppose if you're very good at sort of working backwards, you might be able to reverse engineer a homework solution from this. But we're going to do a slightly more complicated case here to show you where PDEs can arise in practice even when you might not, initially think about it. So for Laplace's equation, the idea here, remember that 4 or 5 weeks ago, we were all about these interpolation problems, right? The idea is I have some function which is sampled at a set of points, and now I'd like some reasonable way to fill in values of that function everywhere else on a domain, yeah? But for the most part, the interpolation that we were doing was in just Rn, right? In fact, for the most part, it was just on a line, including your homework, right? So, and on a line, you have this nice structure that every point on a line is next to only 2 other samples, yeah? But obviously, if you go into higher dimensions, that's not the case. So one application of PDE, which shows up a lot in computer graphics, for example, is when you have to interpolate on a weird domain. So for example, let's say that I draw some strange shape on the board here, right? And somebody has given me, and I know that there's some f of x. Now x is a vector, right? Because it's a point inside of this little blob here. Yeah? We'll call the blob omega, by the way, sort of standard notation. Now, we know that there's some function f of x in the interior, but somebody has only given me f of x on the boundary of omega, and my job is to interpolate it into the inside. Yeah? It's a very reasonable task. So a lot of times, for example, maybe you'll have some little sensor, some robot that's rolling around, and as he rolls around, he collects data about the boundary of some region, and now you want to kind of predict what happens in the interior. Yeah? So, by the way, we'll label the boundary of omega partial omega. I don't really know why that notation is standard, but it is. Yeah? And we're not going to define boundary in any technical way, but it's pretty clear what it means here. Okay. So there are lots of different ways to do this, and in fact we're going to use one that's adapted basically from your homework problem, or something very similar. And that's, in CS205A we have we've covered a ridiculous, stupidly large amount of mathematical tools in this class. I know that. But really they all boil down to about two things, and one of those two things is least squares. And we'd like to keep shoving all of our square pegs into these round holes and making our problems all look like things we know how to solve. Right? But we have this kind of funny problem, which is our unknown here, again, isn't a point, it's a function, but we still like to solve a nice least squares problem that fills it in. Hopefully the story is familiar, we've seen it a few times now. Yeah? Well, one thing we could do, if we want to continue using hammers that we know how to use in CS205A, is write down some energy thing and try and minimize it. And in fact, that is the standard variational strategy for interpolating a function f of x into the interior. So in particular, let's say that I have some f of x, right? And I map him to his gradient f. And remember, this thing is a vector field, if this thing is just some scalar function. Now, if f is like some super wild and crazy function that's like oscillating every which way and going up and down, what do you think the norm of this gradient is going to look like? It's going to be awful big, yeah? Because you see, there's lots of, the gradient is nothing more than the slope, right? It's just a high-dimensional version of slope. And if you have a function that's oscillating every which way, then it's got to have high slope because you've got jammed packed inside of this thing lots of information and lots of changes, yeah? Similarly, if f is this very smooth, low-frequency object, right? So f is just some nice function, right? You can see that he's got very little slope. It's a nice flat thing, right? So with that in mind, our favorite mathematician, my favorite, because he did lots of geometry, is a man named Differential, and he defined an energy, which takes in a function f, right? So no longer just a point in Rn, but a whole function on this entire domain, and gives back a number which measures how smooth we think it is. Yeah? And this energy looks like this. E, usually, by the way, this E doesn't stand for expectation. I never would have even thought of that except a friend of machine learning that's all confused. Right, so this energy of F, well, we're going to integrate over the entire domain omega the norm of grad F squared. Right? Now what does this do? This says that every point inside of omega, we're going to compute the gradient of f, and we're just going to take his norm, and we expect the norm to be small if f is a nice smooth function, and big if f is a wild and crazy function, and we're just going to sum it up over the entire domain, right? You can think of an integral as just summing over lots of points. Yeah? So again, we expect e to be small when f is a nice smooth function. Yeah? In fact, when f is a constant function, what is e?